So chapter 3, third day. Now what we're looking at here is this thing that we're going to call the first derivative test. And we'll apply this a lot of times as this year goes on. First derivative test, and what it does is it's a shortcut or a way, if we don't have enough information, to figure out where a function has relative extrema. Notice it says relative here and not absolute. So we've got this theorem, and this first derivative test I'm going to explain in just a second, but this is what happens. So translating all this, if f prime of x is greater than 0, so if my derivative is positive for all x's in an interval, in between a and b, so this is an interval, not the coordinates of a point, for all x's that are in between a and b, if the derivative is positive, then my function, my f, is increasing on the interval between a and b. So if the derivative is positive, that means the function is increasing. If the derivative is less than 0, if the derivative is negative in an interval, then my function is decreasing in that interval. If my derivative is equal to 0 for all x's in an interval, then my function is constant on the interval between a and b. Well, how do so what does that mean for my first derivative test? Well, my first derivative test says if my function changes from increasing to decreasing. Well, let's make a quick drawing of what that would look like. If your function changes from increasing to decreasing, well, what did I just figure out? Well, then the point at which this happens, C, we'll call it C and f of C. Well, the place that happens, well, that would be a relative maximum. So what I'm doing is I'm narrowing it down. So this first derivative says if I can figure out the place that it changes, that this function changes from being increasing to being decreasing, then I found a relative maximum. If I find the place that it changes from, it's interesting that I have increasing to decreasing on both of these. I would think that we'd want to make this one decreasing to increasing. Sorry about that. So if the function changes from decreasing to increasing at x equals c, then my point that I'm talking about this time, c, f of c, would now be a relative minimum. So what we're going to do with this first derivative test is we're going to try to create intervals, narrow down where the function's increasing and then decreasing, so that we can isolate some of these relative maximums and minimums. Or as it says up here, we're going to isolate the relative extrema of the function, whether they be maximums or minimums. So what does that mean? Well, we can start out with this extrema, this function, fx equals x squared minus 4 to the 2/3, x squared minus 4 to the 2/3. I'm going to guess that most people don't know what that looks like as a graph. So here's what we're going to do. Well, I don't think it has any asymptotes because it doesn't have a denominator. And we're taking, let's see, so to the 2/3 power would mean that we're squaring, and then cubed rooting, which means it's going to exist everywhere. So we're supposed to just find the highest and lowest. So we're going to try to make a graph of this in a little bit. So we're going to start by taking the derivative, f prime of x. So what we're going to do, f prime of x, so 2/3 quantity x squared minus 4 to the negative 1/3, and we're doing chain rule, so then we got a 2x in here. Clean all that up. How about a 4x on the top and a 3 and an x squared minus 4 raised to the 1/3 power in the denominator. So there we've done it. Now, we are looking for the place that this function changes from increasing to decreasing, or vice versa. So that's going to happen. Relative extrema, if you'll think back a couple of days, you'll recall that relative extrema have to happen at critical numbers. How do you find critical numbers? You set your derivative equal to 0, or you find where it's undefined. So we're going to do exactly that. So we're looking for our critical values. So critical values, well, I'm going to start. I would have horizontal tangents in this problem at 4x equals 0, or at x equals 0. And I would have vertical tangents in this problem when the denominator equals to 0. So what's going to happen if you set 3 and the quantity x squared minus 4 raised to the 1/3 power equal to 0, well, you could divide by 3. You could divide by 3, you still have a 0 on the right. Cube it, you still have a 0 on the right. The only thing we really care about is where x squared minus 4 is equal to 0. So that's going to tell us that happens at x equals plus or minus 2. So we have two potential vertical tangents, and we have one horizontal tangent. So here's what we've just come up with. We got something going on at -2. We got something going on at +2, and we got something going on at 0. We just need to figure out what. So the first derivative test, we're going to now invoke this first derivative test. First derivative test says, if you can find an interval, sorry, let's scroll this up so you can see it. If you can find an interval where the function is increasing and then becomes decreasing, you found a max. You found, go from decreasing to increasing, you found a min. So what we're going to do is we're going to set up some intervals. So let's make some intervals. Well, any problem that you start with always begins with at least one interval, and that interval starts at -infinity for x values and goes to +infinity for x values. Well, with each critical number is going to help you partition that interval into smaller intervals. So our first interval always starts at -infinity and goes to our first critical value. What's our first smallest critical value? Our smallest critical value would be -2. Our next interval starts again at that -2. And it goes until our next critical value, which in this case is going to be 0. Our third interval would pick up at 0 and go until our third and final critical value, which would be +2. And our last interval would start at 2 and finish off at that infinity. And forgive me for squishing all of this stuff together. So I'm gonna try to isolate this a little bit because this is meant to be some different work. So those are my intervals. Now here's what we're going to do. In each of those intervals, we're going to pick a test value. We're going to pick one value that's going to represent every point in that interval. So pick a nice test value in between -infinity and -2. Let's use -3. Pick a nice test value in between -2 and 0. Let's use -1. Here we'll use 1. Here we'll use 3. We're going to take those test values, and we are going to plug them into our derivative. We're going to find f prime of whatever your test value is. And all we care about is, does it turn out positive or negative? If it turns out positive, according to what we set up here, if you plug it in your derivative and your derivative turns out positive, then according to that, if your derivative turns out positive, then your function must be increasing in that interval. And since we used a value like -3, so let's try -3. You take -3 and you plug it into your derivative. So I'm going up to the red up here. Well, that's going to give me a negative number on the top. And if I take -3 and I square it, I'll have 9. -4 is a positive number. Cube root of that's going to be a positive number. Times 3 is going to be a positive number. Here's what I found. I've got a positive number on the top. I'm sorry, a negative number on the top, a positive number on the bottom. That is a negative result when I plug that thing in. Well, what does that mean? If you have a negative result and you're trying to draw your function, if the derivative is negative in your interval, then what happens with f of x in that interval? According to what we set up above, if the derivative is negative in an interval, that must mean my function is decreasing in that interval. Derivative is negative, my function is decreasing in that interval. Take -1, plug it in. Negative on the top, looks like a negative this time on the bottom. So my derivative turns out negative over negative or positive. What does that mean for my function? That means my function is increasing in the interval between -2 and 0. Plug 1 in, positive on the top, negative on the bottom. Negative, that must mean my function is decreasing in my interval. Plug in 3, positive on the top, negative on the bottom. We must have a positive here, and therefore my function is increasing in that interval. So think about what we just found. According to the first derivative test that I think I can keep on the screen here, if my function changes from decreasing to increasing, we just found a relative min. If my function changes from increasing to decreasing, I just found a relative max. If it changes from decreasing to increasing, I found a relative min. Now, where do those values occur? Now we got to work at it a little bit. How do we find those values? Well, we know that there's a relative min at the point, let's see, relative min at the point -2 something, relative max at the point 0 something, relative min at the point 2 something. How do we find the somethings? We take these values and we go back to our original function. So if I want to find -2, well, how do I find this value? I'm going to plug it into my f of x. So if I did f of -2, Go back to your original function. Negative 2 squared is, go back up to your f of x. Negative 2 squared is 4. Minus 4 is 0. F of 2 is 0. That's how I get a 0 right there. F of 0 is going to be negative 4 raised to the 2/3 power, so negative 4 to the 2/3. Negative 4 squared would be 16, cube root of that. So this would be a cubed root of 16, whatever that is a decimal. I'm going to guess it's somewhere in between 3 and 4, probably about halfway in between. And f of 2 is going to give us another 0. So we come over here to our graph. At x equals negative 2, we know we got a dot at 0. At x equals positive 2, we know we got a dot at 0. At x equals 0, we've got a dot at the cube root of 16, which is going to be, let's call it in here someplace. I know it's not perfect. We found a vertical tangent at x equals plus or minus 2, so we got a sharp turn, and it is a relative min. At x equals 0, it's a smooth curve and a relative max. At x equals 2, it's a sharp turn and a relative min. I got a graph that looks something like that, and I just found 3 relative extrema. Relative min here and here, relative max here, and remember the reason that they're sharp is because we found a vertical tangent, and the reason that they're smooth is because we found a horizontal tangent. So anyway, there's your introduction to first derivative test.